power for this? I think I do. Okay. Oh my goodness. Right, so what did I have? I had a two physics. Right, this morning I had a tutorial, then a lecture, then a lecture. Oh, and then a tutorial with you, and then a lecture. Okay, write this down. Yep. Okay, so stuff as normal. Let me just actually fix this here. Right, so what we're looking at now, more about magnetic fields. So we've seen that a moving charge in a magnetic field will experience a force, and you should remember the formula, F equals QVB, and F equals BIL. But what happens if we move the magnetic field? So if we move the magnetic field, does anything happen? Because previously the magnetic field has been stationary, not moving. So a moving charge would experience a force. So what happens if we have a moving field? So here's a simple example. You've got a magnet and you're moving it through this copper wire. And in fact, when you do that, you'll get a voltage. So by moving a magnet around a conductor, you can make a current. You can get a voltage. So this is like the opposite, where you move a current to get a force. By applying a force to the magnet and moving the magnet, you can make a current. So we're like going in the opposite direction here. So this is called induction, when the movement of a magnetic field causes a current. Yes? No? Question?
You can use the magnet to produce like power.
Yes. We'll get to how in more detail later. Okay, got that? Induction. So this is the concept. We're moving the magnet, as you can see in the picture here. Okay.
Yes. Have to put like North Pole or the whole magnet?
No, just it's better if the whole magnet goes through, but it could be just north or both. Doesn't matter. So notice while the magnetic field is moving, a voltage will register on the voltmeter. So electromagnetic induction is the production of a voltage across a conductor exposed to a changing magnetic field. Yeah? Yeah. Okay. So induction is making a current by changing a magnetic field around a conductor. So that is basically what I said. You change the magnetic field and around a conductor, not a conduction. We have two laws that relate to this phenomenon. So the first law is called Lenz's Law, and Lenz's law says that if you make a current, the direction will be opposite the change of the magnetic field. So it's really easier to explain this with a picture as well. So what we have here is if I move the magnet into the copper to the right, this current that is made is spiraling to the left. Can you see? So it's spiraling around to the left because Lenz's law says that the current will move in a reverse direction to the magnetic field's movement. Now notice in this one, when you pull the magnet out, the current then spirals away from the magnet.
The voltage will be same.
Be the same voltage in the opposite direction. You can draw this if you feel like you can draw it. You should write this down as well.
I've seen that in some bus persons.
Yes, it is. KJ, you can't have trouble reading it from there, can you? Can you?
It's blurry, the color.
Dude, you're like 2 meters from the board. I don't even. Yeah, 2 meters, I'd say, yeah.
So when you put the magnet like this, the current goes the other way.
Moving the magnet to the right makes the current in the coil move to the left. It will spiral towards the magnet entering. Yeah? Continue? Yeah. So, that is Lenz's law. Now, so far, basically, we know that we'll make a current move in the opposite direction of the magnet, but we don't know how much of a voltage there will be on the voltmeter, so we don't know what the voltmeter will say. So far we know a moving magnetic field will cause a current to flow in a conductor, and we know the direction of the current is to oppose the field. But we do not know how to calculate the voltage, so we have no idea what the voltage is that we will make. So this is where we use the second law of the two laws, which is Faraday's law. Yep. So Faraday's law is basically says that the voltage will equal to minus N, and the reason we have N is because we can have N coils. The change in the flux divided by the change in the time.
And number of
Oops.
the coils turn.
Got this formula?
Yes.
Yeah.
Yes.
And time would be how much time the coil stay.
Yep. The time this change takes place over. So, the minus is there because of Lenz's law. You don't need to worry too much about the minus, but it says that the voltage will be opposite to the change of the magnetic field. So that's actually Lenz's law, the minus there. So, we know that moving a magnet around a conductor will make a voltage. So can we use this for practical purposes? We certainly can. Like you were saying, KJ, we can use this to generate power. So behold, the AC generator looks very similar to the DC motor that we did last time. In fact, it's nearly the same, but there are some small changes to it, which you should note. So firstly, you manually turn the wheel here. Okay, so you turn this. Now, you realize these magnets are very big. So rather than moving the magnets, we move the conductor here. And if you think carefully about it, you realize it's the same thing. So for example, here is a conductor, and if I move a magnet around it, what happens to the conductor? What do I get? I get a current if I move a magnet around it. But of course that magnet's going to be big and heavy, so rather than moving the magnet, okay, I'll move the conductor, which is the same thing. So, we have this conductor moving. Now, the small difference here is that these two slip rings, they're always in contact, whereas with the DC motor, remember there was a little bit of a gap? These slip rings, there's no gap. So notice that this is a full circle, and this here, there's a little brush touching the slip ring, and as this rotates around, this is always touching the slip ring. And then there's another brush coming out here, touching the second slip ring. So this half here is always connected to this slip ring. So in other words, there's no break. They're in constant contact. And then they're connected to like a resistor, a light bulb, or something like that. So we rotate this around. It's like moving the magnet. We get a current here. So it goes here, the red one goes into this ring, and then goes around, and then goes into this ring here, which goes into the blue one. So this blue half is always on this ring. Again, in the exam, they could and have asked you to draw a generator. So this is your AC generator. The names, please notice, these are called slip rings, magnets obviously, and your carbon brushes again. I can't, this is the best picture I could find. I could try.
You don't have a zoom?
Not in the PDF, but I've just got the JPEG. Fields. Okay, so this is like our third picture, isn't it? No, that cannot be it. No, hang on, why are you coming in half an hour late nearly? No, you're too late to come in now. Half an hour is a joke. Half an hour late for class. For a 1 hour, this is a 1 hour class, isn't it?
Yeah.
Yeah, you're not coming in this late now, yeah, come on. I'll talk to Connell later. Right. Got that?
No.
Got it? Oh, come on.
It's not either, Bob.
Hmm? Did you break something? Okay? Yes? No? Okay. KJ, is your one terrible? Show me. Oh. That won't fly in the exam. Okay.
Just
Let's see yours.
Huh?
Let me see yours.
Are you sure you want to see?
Yeah, show me.
You want to have the rights?
Yeah, okay.
Seeable.
I'm moving on, Fahad. Everybody else is finished. We're all waiting for you. You'll have to copy it from the video or something. Okay. So, remember that voltage is, well, this formula from Faraday. Now basically the flux, remember the flux is BA. And let's just ignore the minus N for a moment. How does the BA change? How does the BA change? Well, if you think back to the last lesson, when what we have is, if I draw it here, do you remember in the last lesson we had the formula F
equals E1.
well we had F equals which one was the last one we did with the cosine? If that was the what was it?
Linkage, magnetic
The linkage. It was N. No, not the. I have the wrong letter.
NBA cos theta.
NBA cos theta. That was the flux linkage, wasn't it?
Yeah.
Which I'll just write as the flux here. So the N, the B, and the A, they don't really change. But this is what you do when it's at an angle. So here, this is at an angle to the field. So anyways, my point is, when you start moving things at an angle, the N, the B, the A, they stay the same, but it's the theta that changes. So previously you had flux is, now let's just forget about the n for a moment. Flux is BA, but when it's at an angle, it's BA cos theta. The reason I'm saying that is here, the change is a cos theta. So from the last lesson, all we need to do is add in a cos theta when it's at an angle. So we just add in a cos theta, that's how the BA changes. So we get this formula. So instead of BA, we have BA cos theta. But how does the cos theta change? In other words, the BA is constant. How does the cos theta change? What is delta cos theta over delta t? How does cos change? Well, it's the derivative of cos. What's the derivative of cos? Minus sign. And again, we'll just forget about the minus for a moment, so it's sine. So really we need to know how the cos changes, and well, that's a sine, which you know from math class. So all this explanation, what I'm trying to say is your graph for voltage, well, I'll have a nice graph here, will have this shape. So when the generator area is vertical, we have no voltage. And then when it rotates around to 90, now you might be thinking, wait, why is he saying this is 0? Remember, the angle is the one perpendicular to the plane. So this angle here is horizontal, so that's 0. So when this, or maybe we'll put it this way to the right, so that's 0. So when this flips around to 90, that's when you have most voltage from the generator. Then when it flips back this way, again you have no voltage. Then when it flips down, you have voltage, but in the opposite direction, and then when it flips back here, we're back to no voltage. And this shape is exactly a sine. And the reason it's a sine is because of the cos in the formula. Okay? You don't really need to know that part for the exam, but you do need to know that the graph is sine. And you also need to know for the exam what positions the generator needs to be in to get the different points on the graph. So we start off in the vertical position and we rotate. Okay? So please copy this graph and please note the positions here. Yeah?
One after 360.
Huh? It goes back to this.
The 90.
Huh?
Up in 0.
Yes, Peter?
How does, like, where the field faces that this would be like this?
Say again? The field?
Yes.
I think it's from our picture. We have north on the left and south on the right.
Okay. So, like this. This is the parallel.
You've answered your own question?
Yes.
Okay.
What type of this graph?
Yes.
Oh, just the voltage graph for the generator. Yeah? So, interestingly, the voltage increases and decreases and changes direction. So the voltage goes up, goes down, and changes direction. That's interesting because previously we've just been looking at a constant voltage, or in the case of a capacitor, the voltage decreasing. But we've never seen a graph like this for voltage where it increases and decreases and changes direction. So, if I just go to some paper, this is if I was to connect, or if I was to measure the voltage over there at the plug, I would get a graph like this. We know that this is 220 volts, yeah? But 220 volts doesn't make sense anymore because it's not a constant 220. So what does 220 represent in the graph? What do you think it might represent? Kind of like an average height of the graph. So here we say, on average it's 220 or minus 220 volts. So that makes you realize, so the maximum voltage is sometimes more than 220 from the power supply. So is there a way to work this out? Well, there is. The maximum voltage is equal to the square root of 2 multiplied by the average voltage, and this is often what is said on electrical appliances. So in Ireland we're at 220, in America they're at 110. So if I do 220 times root 2, that means the voltage hits as high as 311 volts on the peaks, and on the troughs as low as minus 311. So this is why root 2? It's a maths thing.
In gas we have both.
That's fine. There's no problem with me. I don't have a problem with that. The root 2, see KJ, it has to do with integration of sine. Yes. We've done integration, and we've done integration of sine squared. This is not on the course, but since you're curious, when you have something in physics which is changing, and you want to know what the average value is, one way you could get it is by squaring the function, integrating it, and I think we have, if it starts at A and finishes at B or whatever, we have a 1 over B minus A. So anyways, when you do that for your sine graph, you get the results that, basically that's how you get the root 2 to appear. This is too advanced for the IFY physics, but maybe on university level you can see the proof of how the root 2 appears. But it is a root 2 for a sine graph. Okay. So we have this new current called AC. Previously we've actually been dealing with DC, where the current just directly and constantly moves in one direction at one value, except for capacitors where we've seen the current decrease. AC is called alternating current, and this is when the current changes its direction, whereas in DC the flow is in one direction. So this is the difference between AC and DC. Okay, got that? I guess. Yeah? Oh, goodness. Okay, finally, do we have a handy way to figure out which way the current will flow? So when we move a magnet, so here's my magnet and here's my conductor. So when I move a magnet over a conductor, which way will the current flow? Well, you kind of know from Lenz's law, it'll be in the opposite direction of the magnet. But what I mean by this is when you have it in the generator. So when you have, oh sorry, not that way around. When you have this spinning in the generator, which way the current will flow. So we have this thing called Fleming's right-hand rule, not to be confused with left-hand rule. The left-hand rule is when the charge is moving in the magnetic field. This one is for the generator. So here, this is the motion or the force to turn the generator. This is the magnetic field, and this is the current. So if I go back to my picture, so in this one, force is going up. Well, if we look here at blue, which way is the force going to make this wheel turn? It's going up. So up it is. Okay. Which way is the magnetic field going? North to south. So that would be going this way. So the current should be going into the page on this finger here, which it is. Current's going into the page. Fleming. Yeah. So Fleming's right hand for the generator, left hand for the QBB. Okay. So if we look at the red one here, need to go to the other side. So the force this time is going down, and the field is going to the right. No, hang on. Force is going down. Field is going to the right. So the current, the current is going to you, which it is in the picture. So this is Fleming's right-hand rule. You can try and draw it, or at least write down the name of the rule so you can get a picture of it. Are you drawing it?
Yeah.
Good man. Okay, so we'll just and then another final hint. So when the flux changes, it can change two ways. Either the B changes or the area changes, because remember flux is BA. But for our problems, usually we don't have to deal with both changing, which is good. So we either have area multiplied by the change in the density, or density multiplied by the change in the area. The change in the density is if the B changes, of course, and the change in the area is if the area changes. Now what exactly does that mean? Well, usually it's swapped out area. So what I mean by that, we can do two things. So for example, we can have a conductor, then we can have a big magnetic field, and then all of a sudden we can make the magnetic field smaller. So that's B1 and that's B2. So what changes here is the B. So the change in the flux would equal the area times B2 minus B1, because the B changes. Whatever the area is, whatever the shape is. But another thing you can do is you can keep the B the same, and like with the generator or whatever, you can have something like, imagine a piece of copper here, and imagine I move the copper down. So here's my copper wire, here's the magnet. So I have two choices. I can move the magnet, I can make the magnet stronger or weaker. This will make a conductor here. So if I do this, no magnetic field, I get a current, and then when I remove it, I get a current again for a short time. Or I could move the conductor. So the area here is the area that the conductor sweeps out in its movement. So, for example, if I move like this, the area will be like the box. The change in the area is like how much area I make per second. So, for example, here, if I move my conductor down at 1 meter per second, and this is 1 meter wide, then how much area do I get each second? 1 meter squared. Yeah. So the delta area is 1 meter squared per second. Okay? So what I'm saying is there's two ways to do this. You can either change the magnetic field or move the conductor to change the area. You get both in the exam. Okay? So we'll have to split this lesson over two because I haven't got time to do the examples. So we have two examples to look at, and then some questions here. But anyways, I mean, if you want to watch the video and try the questions, that's fine. But without the examples, I don't think you can do it. So we'll just break this lesson up into two parts. All right.